So now we're gonna be going over the multiplication algorithm. The algorithm is fairly simple. So when we see multiplications, if it's within 10 by 10, so let's say 6 times 3, then automatically we know that that's just 18, right? Because I assume that we have already memorized the results of the multiplication table, because that's going to make computation just a lot more efficient down the way. So I really encourage you to try that and memorize the whole multiplication table. But anyway, it gets slightly more involved when we take a look at double digit addition, I mean multiplication. So, for example, if we were to say multiply 17 by, okay, by let's say 16, all right, this it's pretty difficult to even begin thinking about because if you go by the definition of multiplication that we were taught, it's going to be 17 plus 17 plus dot 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 17 with a total of 16 17s. So this is obviously very inefficient and it's going to take a while for you to add up all those 17s. But in fact, there is a pretty clever way to to multiply these two numbers. So we can begin by really thinking about what 17 and 16 means, right? So we've done this trick before in the previous video where we rewrite 17 as some addition, right? So 17 we can rewrite it as 10 plus 7, right? That makes sense. And 16 we can rewrite it as 10 plus 6 in a similar fashion, very similar. All right. So now we can do we can rewrite this expression as something in this form. So we can use the substitution. We get 10 plus 7 times 10 plus 6. All right, good. Okay. So now how do we do this? So we can sort of think of this as 10 plus 7 times 10 plus 6 is going to be something like this times this thing, right? And then this times this thing again. So we can expand this and we get 10 times 10 plus 6, all right, plus, because this plus is maintained, let's just draw here so we know, 7 times 10 plus 6. Good. Okay, so, and then we can expand this even further into this 10 times 10. I use this dot to mean multiplication, plus 10 times 6, plus, this is the original plus here, 7 times 10, plus 7 times 6. Alright, what do you notice here? Well, we notice that we have sort of simplified everything. Alright, in the sense that we no longer have like 17 and 16. Instead, we have like 7 times 6, which we already know how to do because we know the 10 by 10 multiplication table. And this is 7 times 10, which we should know how to do because this is effectively just 7 times 10 with a 0 tagged on at the end. So this will be like 70 because that's 7 times 1 and this 0 comes from here. Alright, and 10 times 6, again, we should just know how to do this because this is effectively computing 1 times 6. So we get 6 and 0, which is 60. And this is 10 times 10, which it's somewhat tricky to think about, but it's just 1 times 1, right? With 2 zeros stacked behind, so it's 100. Right, and then 6 times 7, we know is 42, right? 6, 7. And then we can add these because, again, we just have to carry the add down. And then we can, yeah, this just turns into an addition problem. So, yeah, we can add it. We get 160. This becomes 160. This becomes 112. And then we can add these two. So it's going to be 272. All right. This is our answer. So it's going to be pretty tedious and space intensive to write this out every single time. although this is in principle how you will actually do this. But so there's a nice cleaner way that we can write this, just like how we can write the addition algorithm. So we can notate it as something like this: 17. Let's write a bit smaller. 17 times yeah, let's do this. 16. Yeah. So this is very similar to the addition algorithm, just like this. But it is somewhat different. But it's again in principle the same thing as this. All right. So basically, again, we can compute 6 times 7. So 6 times 7 will be 42. Right. So this is effectively this result. And then we have to compute 6 times 1, which is effectively this result. So this is 6. 6 plus 4 is 1. 6 plus 4 is 10. So this is just 10. And then here we have 1 times 7, which is this result right here. And so that's going to be 7. Right? We have to write it in this place because it's technically 10 times 7. Right? But we are sort of covering it up by 6 here. So we just imagine it's 1 times 7 instead. And this is 1 times 1, which is effectively this result. It's actually 10 times 10, but we're just covering it up. So we got that it's going to be a 1. And then we can add them together. 272. Yep, and indeed these two results do agree. But we can actually think about this in a different way, right? Because when we are breaking it to 10 and 7, we're effectively just trying to make it nice in the sense that we bunch together the 10s and bunch together the 1s. So, but we can do this in a separate way because 17 can be also written as 20 minus 3. Right, this is 17. And 16 can be written as 20 minus 4. Right, and then this is effectively the same thing. We can do 20 times 20 minus 4 times 20 minus 3 times 20. And then note here, negative 3 and negative 4, this is actually plus 3 times 4 because double negative will be positive. Alright, so this is 400 because this 2 times 2 is 4, and then 4, there's 2 zeros tagging along right here. And then 4 times 20, this is going to be 80 because this is effectively 4 times 2, which is 8, and then we'll carry along a 0. And then 3 times 20, this should be 60, again for the same reason. This is 3 times 4 is 12, we should know this. And yeah, so we transform this into a subtraction problem instead of an addition problem. Alright, this is pretty cool. So now this we can just subtract. So this and this becomes 320, and then 320 subtracting 60 becomes 260. 260 we can add 12, so we get 272. Yep. So this indeed confirms with our previous results. So that is very nice. And you might be wondering, well, this looks more complicated, and then it looks longer. You have like subtraction and addition mixed together. So like, why is this better? Well, it turns out this is not necessarily better, right? But it is better in some cases. So I will show you one of those cases. Let's say we have 99, all right, times 17. All right. So how would you solve this? If you were to use this, so actually, in fact, let's just use that 99 times 17. All right, if we use this algorithm that we're shown here, 7 times 9 is 63, so we have to write 3 here, 60 here, and then 7 times 6, 17 times 9 is 63 again, so 69. Because it's going to be 63 plus 6, so 69. So 1 times 9 is 9, 1 times 9 is 9 again, so we add it together. 3, 9 times 9, 9 plus 9 is 18, so we have to add 1. By the way, this is the same rule that we showed before, which is it's always going to be 1 less than the number that we're adding to a 9. So this becomes 1 plus 6, which is 7. 7 plus 9, we can use the same trick. We're going to get 16. So this turns out to be 1683. All right, but if we use this trick right here, we're gonna write 99 in terms of 100. So 99 is gonna be 100 minus 1. And then let's just leave the 17 here. All right, so we can just distribute 100 times 17 minus 17, right? Because we have 17 hundreds and minus 17, right? And then this thing is very easy to compute. We can just do 1700 and then minus 17. So this thing is going to be, if you just compute it, it's going to be 1683, just like what we have here. So this is quite a bit simpler, actually. In fact, this tells us a fairly nice thing, which is that if you have 99 times any number, right, let's say k, which stands for like any number, all right, we can think about it as 100k minus k. All right, and this actually extends to pretty nicely to 999, right? Times k is going to be 1000k minus k, which, yeah, it's pretty similar, all right, and it's by the same principle. And what's even nicer is that we can sort of derive our previously established principle of 9 multiplied by a digit number with this same principle. So we can do 9 times k is going to be 10k minus k. So what this means is that, so for example, 9 times 6, right? It's going to be 60 minus 6, which is going to be 54, right? So a quick way to do these to remember, I mean, well, you should really remember these multiplications, but a way of you to remember it if you don't is that you can just think about, like, let's say 9 times 7, you just do about 70 minus 7 and you can get 63. All right. Yep. So this is about all I have for today, and I hope you enjoyed the video. So yeah, thank you for watching.